Hey everybody! Today we are going to talk a little bit more about exoplanets and at the end just a tiny bit about astrobiology and look at some exoplanet light curves. We've already introduced exoplanets, so now let's talk about the ways that we can discover them. We're going to talk about 3 different ways, but really focus on one. So as of this week, there are 4,301 confirmed exoplanets. There's a lot more that have potentially been detected, but you have to spend a lot of time sorting through that data and verifying it. After the planet makes a couple of trips around the star, you have to double check yourself that you've actually caught an exoplanet. So there's a lot of work that goes into verifying that these exoplanets exist. And here's a couple of ways we can do it. These first 2 ways I'm going to talk about, this first one is called direct imaging. And that's where you literally take a picture of that distant solar system. Okay, you can really only see that distant solar system in like infrared wavelengths of light and also radio waves. Very long wavelengths of light because the planets are emitting light in like the microwave and infrared part of the electromagnetic spectrum. But the thing is that whenever you directly image a stellar system, that star is emitting so much light in the visible that it kind of keeps you from seeing those other planets that are orbiting around that star. So what you do is when you have a telescope that takes these images, you put a little, we call it an occulting disk, in the front of where that star is in that stellar system. So there's a little disk that's blocking out the light from the star here, and then it allows you to see the planets that are orbiting around it. So you have to block out all of that light from that star that's washing out all the light you can see from the planets in order to get it. And so finding planets through direct imaging is a really hard thing to do. Here's an example of a system that has been direct imaged to find exoplanets. There are 4 exoplanets here in this picture. So here's the star. There's a little occulting disk in the middle blocking out all the light from that star. And then that lets you see 4 planets, planet B, C, D, and E. Another way we can find exoplanets is by the radial velocity method. And this uses the Doppler effect or the Doppler shift. Sometimes it's also called the wobble method. So we'll see why here. So here we've got the star in the middle, and we've got a little planet that's orbiting around it. Now, the planet star system, that system is going to orbit around what we call the center of mass of the system. The center of mass of the system is right here, marked by the plus sign. So the center of mass of the system is like the average center of where all the mass is located. Okay, you can find the center of mass for you, for your body. The center of mass of any object is where you can take that object and balance it on a point. So here I have an ink pen, or you can try this with any of your ink pens and see where you can get it to balance. Mine is heavier on one end than the other. So my center of mass of the ink pen is going to be closer to the heavier end than it is to the lighter end. And where I can balance that on my finger is the center of mass of my system. So imagine you take a rod and you connect it between the planet and the star. The place where you can balance that rod is the center of mass of the system. And usually for planets, especially for small planets, that center of mass is really close to the center of the star it's orbiting around, but not necessarily the center. Because of the fact that the planets are orbiting stars around the center of mass, whenever you watch the planet-star system, you're going to see the star wobble a little bit. You might not be able to see the planet as well, but if you can see the star wobble a little bit, you can infer something about the fact that there must be other mass there. And so with that, you take the light coming from that star and that planet, and you can infer based on spectroscopy and the shifting of the spectra coming from those 2 objects, whether or not those objects are moving toward or away from you. Radial velocity is the velocity that an object has toward or away from you. And so those are a couple of ways you can get at the fact that there's a planet orbiting a star. And so let me just play this as a little depiction here. You can see that that planet is orbiting around the center of mass of the planet-star system. But if you're just looking at the star, you're going to see that star wobble around a little bit in the sky. That's another way we can detect an exoplanet. But the way that most exoplanets are detected these days is through the transit method. And we are going to look a little bit at this in lab this week. So during the transit method, we look at what we call the light curve of the star. So what we're going to see right here is the light curve of the star. And as our little exoplanet passes in front of the star, that exoplanet is blocking a little bit of light from the surface of that star. And then that changes the light curve. It gives us a little dip in the light curve. So let's watch. So here we have the brightness of the star. Now our planet right there just passed across the disk of the star. And then we've reduced the light curve that we get from that star. The planet's going to keep on moving across, okay? And we see still this maintaining this dip in the light curve, and then the planet's going to come off the edge of the star. We call the edge of the star the limb. And as it does that, then the light curve from that star comes back to normal again. So this is how we find planets around other stars through the transit method, by watching if we can find these dips in the light curve. If we find the dip in the light curve, we can infer that there's a planet there. And how deep that dip is and how wide that dip is tells us something about the size of the planet and the distance that that planet is away from its star. So here we have two light curves from two different stars, but they both have a planet of the same size transiting across them. So here we have a G dwarf, a star like our sun. Our sun is a G-type star, a G-type dwarf. And a lot of the stars on the main sequence, if they're not a giant star, we refer to them as dwarfs. This planet, when it passes in front of one of these larger G-dwarf stars, it doesn't block out as much of the light relatively. So we only get a little tiny dip in that light curve. But that same size planet, that planet, like the planet to star ratio, is different whenever that same size planet is passing in front of a smaller star. So if that same size planet is passing in front of a smaller star, that planet is going to be blocking out more of that star's light than it does whenever it passes in front of a larger star. So whenever that planet passes in front of the smaller star, we're going to see a bigger dip in that light curve. So actually it's a little bit easier to find planets orbiting around these smaller M-dwarf stars, because usually the planet to star ratio is such that the planet is larger compared to the star than it is for stars that are a little bit bigger. Now we're going to look at a couple of equations to help us quantify these light curves, and actually we can get at the radius of the planet in this way by looking at the light curves. So in a planet transit, the planet's circular disk blocks the light of the star's circular disk. And we've talked about that. The amount of light the planet blocks is called the transit depth. The transit depth is just the ratio of the area of the planet to the area of a star. Imagine that the planets and stars are such far distance away from us that we're assuming that the star, we can just represent the area of the star that's facing us as a circle, and the area of the planet that's facing us as a circle. The area of a circle is pi times its radius squared. So the transit depth is the ratio of the area of the planet to the area of the star, at least the cross-sectional area of the planet to the cross-sectional area of the star. So on top here, we have the area of the planet, pi times the radius of the planet squared, divided by the area of the star, pi times r squared, the radius of the star squared. Okay, so the pi's cancel on top and bottom. So then you're left with just the transit depth is the radius of the planet squared divided by the radius of the star squared. And then we can also write this in another way by just saying the radius of the planet divided by the radius of the star squared. That's what we call the transit depth. That tells us how deep here is our light curve going to get when that planet passes in front of it. Now we can use this transit depth to help us, because we can, from observations, get this transit depth. How deep is this dip from the average brightness of the star? And with that, we can find the radius of that planet, okay? So the deeper this dip, the bigger that planet is relative to the star. So if all of this, our planet over our star squared equals the transit depth, we can solve this equation for the radius of the planet. So the radius of the planet equals the radius of the star times the square root of our transit depth. So if we know the radius of the star from observations, we know the transit depth from the light curve as the planet is passing in front of the star. So this will be the transit depth. Then from that, we can figure out what is the radius of that planet that's making that dip in the light curve. And that's a really important and useful tool for astronomers who are trying to study exoplanets. So remember what we called the transit depth. How deep is this dip in the light curve tells us the size of the planet. The bigger that dip is, the bigger our planet in size, okay? And then how broad that dip is tells us how far away that planet is. So a planet that is further away from its star is going to take a longer time to orbit around that star. So that planet is going to be transiting across the star for a much longer time period. So we're going to see a broadening of the dip in this light curve as planets are further and further away from their star. Remember Kepler's laws and conservation of angular momentum. The closer a planet is to the star, the faster it's going to orbit around that star. The further the planet is away from the star, the longer it's going to take that planet to orbit. And we have seen that exact same thing in our solar system. Okay, that's Kepler's third law, and we looked at that earlier in the semester, if you can remember. And now we're going to look at the light curves from a solar system called TRAPPIST-1. You've heard me talk about it before, I think. TRAPPIST-1. The TRAPPIST-1 system is about 40 light years away from us. And the TRAPPIST-1 system has 7 planets orbiting around one star. Now that star is the star called TRAPPIST-1, and it's about 10% of the sun's mass, okay? It's really small, it's a red dwarf, an M-type star, one of the tiniest stars, the lower right-hand end of the main sequence branch of the HR diagram. So here we have the TRAPPIST-1 star, and we've got our planets, B, C, D, E, F, G, and H. So there's 7 of them, and they're all terrestrial planets. And when you label exoplanet systems, you start with B. B is the closest planet to the star, and then C is the next planet out, D, E, F, G, H, and so on, okay? Now, the TRAPPIST-1 system is really tiny, actually. We've got these 7 planets orbiting around that star, and all of those planets orbiting around that star can fit within the orbit of Mercury in our own solar system. That's really crazy. So imagine we were talking about the size of our solar system, but this TRAPPIST-1 system, even with 7 planets packed around that star, that whole system can fit within the orbit of Mercury. So here's our TRAPPIST-1 system. That whole thing fits inside Mercury. Here's our solar system. We've got Mercury, Venus, Earth, and Mars around the sun. Okay, it's a really intimate, tightly packed solar system. And then here for comparison are the orbits of Jupiter's Galilean moons around Jupiter. So you can see in comparison to that as well. Now these are the light curves for TRAPPIST-1, for the TRAPPIST-1 star. So these are the light curves of the star. So here's the average brightness of the star here. And then each one of these dips is from one of those planets transiting in front of the star. So each one of these dips in the light curve corresponds to one of those planets passing in front of the star. Okay, so now these light curves, there's 7 of them, right? Because we have 7 exoplanets transiting in front of that star. So these light curves are ranked in order of smallest to largest planet by radius. So remember that the size of the planet in radius is reflected in the dip of the light curve. How deep is that depth? The depth of that light curve, okay? The deeper that dip in the light curve, the bigger that planet is. So we can look here. On top, we have the smallest one of the TRAPPIST-1 planets, And on the bottom, we have the largest one of the TRAPPIST-1 planets, largest by radius. So you can see that as we go down, well, some of them are kind of hard to see, but generally you can see the trend that as the radius of the planet gets bigger, we see the dip in that light curve gets deeper. That's our transit depth. So here we are, TRAPPIST-1H is the smallest of those 7 planets, and it has a radius of 0.76 that of the Earth, 76% of our Earth's radius. The next largest one in size, 77% of the Earth's radius. Then the next one, 92% of the Earth's radius, and so on. And the largest one of the TRAPPIST-1 planets has a radius of 1.13 times that of the Earth, 113% larger than our Earth's radius. As we go down here, we see generally that the dip in that light curve, the transit depth, gets larger as our planets get larger, okay? And then here, we've got the TRAPPIST-1 light curves ranked in order of closest to the star to farthest away from the star. And so we said that the further out a planet is from the star, the longer it takes that planet to transit in front of the star. So if our horizontal axis is time, the closer a planet is to the star, the less amount of time it's going to spend transiting in front of that star. The broader the dip in that light curve, the further away that planet is from the star, okay? So we have the closest one in, which is how we label the planets, the closest one in, TRAPPIST-1b, and then C, D, E, F, G, and H. And you see that as we get further away from the star, the width of this dip in the light curve gets longer. So let's calculate the transit depth for a star the size of the sun with a gas giant the size of Jupiter that's transiting across it. So remember, the transit depth is equal to the area of the planet divided by the area of the star, at least the cross-sectional area of each of those that are facing us with our observations. And we can get rid of the pi's on top and bottom, and we can simplify the equation. The transit depth is equal to the radius of the planet divided by the radius of the star squared. So the radius of Jupiter is 71,400 kilometers. We're going to divide that by the radius of the star, our sun, which has a radius of 695,700 kilometers. So the units of kilometers cancel on top and bottom. We have to square that whole thing. So you take 71,400, divide it by 695,700, get that fraction. And then you square it, you raise it to the power of 2, and when you do that, you find that the transit depth, imagining our solar system as an exoplanet system, and maybe some other alien civilization is looking at our star and looking at the planets transiting in front of it. So the transit depth for Jupiter going in front of our sun would be 1% or 0.01. 0.01, 1% of the light coming from our sun gets blocked out by Jupiter when Jupiter passes in front of it, okay? So that's what that means. And this is something that would be easily detected by Kepler, the Kepler Space Telescope. So if a nearby intelligent civilization launched a telescope like Kepler and looked toward our solar system, they'd be able to detect Jupiter orbiting around our sun.